Proxima Centauri, the closest star to our solar system, has long been a subject of fascination for astronomers. This small red dwarf, discovered in 1915 by Scottish astronomer Robert Innes, is part of the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite its proximity, just 4.24 light-years away, it remains invisible to the naked eye due to its relatively low brightness. However, Proxima Centauri holds immense scientific value, especially as the host star of Proxima B, an exoplanet that orbits within the habitable zone of the star. Dwarfs like Proxima Centauri are smaller, cooler, and much longer-lived than stars like our Sun. Their low luminosity makes them challenging to observe, but it also means their habitable zones are much closer to the star. For Proxima Centauri, this translates to an orbital distance of just 0.05 astronomical units, a mere fraction of the distance between Earth and the Sun. This close proximity exposes Proxima B to intense stellar activity, including frequent flares and high amounts of radiation, conditions starkly different from Earth. The discovery of Proxima B was a monumental achievement in exoplanet research. Using the radial velocity method, astronomers detected subtle wobbles in Proxima Centauri's position caused by the gravitational pull of an orbiting planet. These wobbles allowed scientists to determine the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed that Proxima B exists, marking a breakthrough in the search for worlds beyond ours that might be habitable. While ground-based observations have been helpful, they also come with limitations. Light interference and atmospheric distortion hinder Earth-based telescopes' ability to capture detailed data about the planet's surface or atmosphere. Most of the information we have, including its volume, orbital distance, and other characteristics, relies on indirect measurements. To uncover deeper truths about Proxima B's surroundings and its potential for life, more advanced instruments like the James Webb Space Telescope, JWST, are crucial. Proxima Centauri's role as a gateway to understanding systems of exoplanets cannot be overstated. As the closest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima B, in particular, represents an enticing possibility, a rocky planet the size of Earth with the potential to harbor water and maybe even life. However, the planet's harsh environment makes it a complex puzzle. The James Webb Space Telescope is more than just another tool in astronomy's arsenal. Designed to take over from the Hubble Space Telescope, JWST was envisioned to overcome its predecessor's limitations and push the boundaries of human knowledge. While Hubble has provided invaluable information about the cosmos, its capabilities are constrained by its focus on visible and ultraviolet light. JWST, on the other hand, is designed to observe the universe through infrared wavelengths, allowing it to peer through cosmic dust and uncover phenomena invisible to Hubble. One of the key aspects of JWST's design is its mirror, which spans a staggering 6.5 meters in diameter, more than double the size of Hubble's mirror. This larger mirror enables JWST to gather significantly more light, putting it in a position to observe extremely faint and distant objects. Coated with a thin layer of gold to improve infrared reflectivity, the mirror is composed of 18 hexagonal segments that work together to create a highly sensitive observational platform. Another first-of-its-kind innovation is the sun shield, a layer that keeps the telescope's instruments at a constant temperature of about -233 degrees Celsius. This extremely cold environment is crucial for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the L2 Lagrange point, a secure location about 1.5 million kilometers from our planet. This reduces interference from Earth's heat and light, allowing JWST to continue its observations. The telescope can study everything from the earliest galaxies to the atmospheres of exoplanets like Proxima B. Its focus on infrared light is particularly significant, as it allows astronomers to study redshifted objects, whose light has been stretched to longer wavelengths as the universe expands. JWST's capabilities extend far beyond mere observation. It is designed to answer some of the most profound questions in science, including the origins of galaxies, the formation of stars, and the conditions that might support life on other planets. With state-of-the-art instruments, including the near-infrared camera, NIR-CAM, the mid-infrared instrument, MIRI, and the near-infrared spectrograph, NIR-SPEC, JWST is not only a telescope, but also a time machine, laboratory, and testament to human ingenuity. Proxima B has captivated scientists and the public alike as the possibility of a second Earth. Located within its star's habitable zone, the planet may have the right conditions to support liquid water, a key ingredient for life. With a mass roughly 1.17 times that of Earth, Proxima b is likely a rocky planet similar in composition to our own. Its distance, approximately 4 light-years from Earth, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima b is far from a perfect twin to Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual daylight while the other remains in eternal darkness. This creates a unique environment with extreme variations in temperature between the two hemispheres. The region where day meets night, the terminator line, may provide a confined twilight zone with moderate conditions that could support life. Still, the challenges posed by Proxima b's environment are significant. Its host star, Proxima Centauri, is known for intense solar flares that emit bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to harsh conditions. If any atmosphere remains, it likely requires a strong magnetic field to shield it from radiation. Without such protection, the surface environment would be hostile to life as we know it. Despite these challenges, scientists remain optimistic about the potential for life on Proxima b. The planet's location within the habitable zone suggests that liquid water could exist, either on the surface or in subsurface reservoirs. Life might adapt to the harsh environment in the same way extremophiles do on Earth, organisms that thrive in extreme environments like deep-sea hydrothermal vents or areas with high radiation. These adaptations could include radiation resistance, subsurface habitats, or unique biochemical processes. The search for life on Proxima b is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions. Are we alone in the universe? Proxima b symbolizes a tantalizing possibility, a rocky, Earth-like world that might harbor the conditions necessary for life. As our technology advances, so too does our ability to explore this intriguing planet and uncover its secrets. While Proxima b presents exciting possibilities, its environment is profoundly influenced by the nature of its host star. Unlike our Sun, Proxima Centauri is a red dwarf, smaller, cooler, and significantly dimmer. Its diminutive size and temperature mean that its habitable zone is much closer in, pulling Proxima b into N. These solar flares pose a serious threat to any potential life forms on Proxima b. The flares release high-energy particles, X-rays, and ultraviolet radiation that can erode a planet's atmosphere over time. Without a strong magnetic field or a thick atmosphere, the planet's surface would be bombarded by harmful radiation, making it difficult, though not impossible, for life to survive. Despite these dangers, researchers have not ruled out the possibility of life. Some theoretical models suggest that a strong magnetosphere, if present, could deflect harmful radiation, while a dense atmosphere could absorb and scatter dangerous particles before they reach the surface. Life could also take shelter beneath the surface, in oceans, caves, or even within rocks, just as some microbial life does on Earth. Scientists also speculate that if Proxima b has significant geological activity, it might help regulate surface conditions. Volcanism, for example, could replenish atmospheric gases lost to solar wind and flares. This process, known as outgassing, could play a crucial role in maintaining a stable climate over long periods. Another exciting prospect is the potential for liquid water. If water exists, it may not be on the surface in large oceans as on Earth, but instead locked beneath layers of rock or ice. Subsurface oceans, similar to those hypothesized on moons like Europa or Enceladus in our own solar system, are possible candidates for hosting microbial or even more complex life forms. In the coming decades, future missions and observatories will aim to gather more detailed information about Proxima b and similar exoplanets. One of the key goals will be to detect biosignatures, chemical indicators like oxygen, methane, or water vapor, that might point to the presence of life. The James Webb Space Telescope will be central to this effort, alongside other planned missions like the European Extremely Large Telescope, EELT, and the LUVOIR and HABEX missions proposed by NASA. These instruments could provide the resolution and sensitivity needed to analyze exoplanet atmospheres and search for traces of life-related chemistry. As our ability to detect and study exoplanets improves, Proxima b remains one of the most promising candidates in the quest to find life beyond Earth. Its relative proximity means that one day, with future technologies such as interstellar probes, we may even be able to send a mission directly to the system to collect close-up data. Projects like Breakthrough Starshot have proposed using light-sail spacecrafts powered by ground-based lasers to travel to Alpha Centauri. If successful, such a mission could reach the system within a human lifetime, opening the door to the first-ever exploration of a planet orbiting another star. The discovery of Proxima B is more than a scientific milestone. It's a reminder of how much we still have to learn about the universe and our place in it. Whether or not Proxima B ultimately proves to be habitable, it continues to inspire dreams of exploration, innovation, and the possibility that we are not alone. Doses of radiation and events like ultraviolet radiation are significantly more prevalent and potent in red dwarfs, as opposed to stars like our Sun. Proxima B refers to a constant bombardment of high-energy particles, which could strip away the planet's environment over time. Without a magnetic shield, any atmosphere on Proxima B would be vulnerable to erosion, leaving its surface exposed to harsh radiation. Even if Proxima B retains some of its atmosphere, the radiation from Proxima Centauri poses life-threatening obstacles. At high levels, ultraviolet light can fracture molecular bonds, preventing the formation of complex organic compounds. This would severely restrict life's potential to develop or remain, depending on the organisms. On Earth's surface, such as Deinococcus radiodurans, organisms have developed mechanisms for repairing DNA damage caused by radiation, implying that life can exist under extreme conditions. However, Proxima B may also adapt. The degree of resistance to radiation required would be extreme, possibly requiring completely new biochemistries. Proxima's curiously tidally locked nature may offer some protection. Whereas one hemisphere experiences constant radiation from Proxima Centauri, the planet's dark side could serve as a refuge. Caves or subsurface habitats could protect potential organisms from the worst of the radiation. Similarly, if Proxima B has subsurface oceans, they could provide a stable, radiation-free environment where microbial life might thrive, much like the ecosystems around hydrothermal vents on Earth. Despite these challenges, scientists remain hopeful that Proxima B's extreme environment offers a one-of-a-kind opportunity to study the adaptability of life. By looking at how organisms might survive, or even thrive, in such a situation, researchers can improve their understanding of what makes a planet habitable. Proxima B is not just a potential home for life, it is a natural laboratory for evaluating the capabilities of life itself. The planet's proximity to Earth and its location in its star's habitable zone make it an ideal candidate for further study. With new telescopes and instruments, scientists will keep an eye out for evidence of habitability in Proxima B. Though the road ahead is fraught, despite its difficulties, Proxima provides a fascinating glimpse into the possibilities of life beyond Earth. It serves to remind us that our search for knowledge, and for life on other planets, is just getting started. The search for life beyond Earth continues. The study of exoplanets like Proxima B plays an important part in expanding our comprehension of the conditions necessary for life to exist. One of the key factors that makes Proxima B so intriguing is its relatively Earth-like size and makeup, both of which make it an ideal candidate to study the potential of planets to be habitable outside our solar system. Scientists are particularly concerned with locating planets with similar characteristics to Earth because they provide the most enticing environments for life's development. To investigate the possibility of life on Proxima B, astronomers are making use of a variety of cutting-edge techniques to analyze the planet's environment and the composition of its atmosphere. One of the most promising methods is the study of exoplanet atmospheres by means of transmission spectroscopy. This technique involves observing the passage of light from a star through an exoplanet's atmosphere during a transit. It has the potential to reveal a chemical analysis of the atmosphere's makeup. The absorption lines in the spectrum of light can be detected by scientists and may indicate the presence of gases such as carbon, methane, and oxygen dioxide, gases often associated with life on Earth. Detecting such gases on Proxima B could provide strong evidence that the planet could accommodate biological processes. Additionally, researchers are investigating the possibility of bacterial life beneath Proxima B's surface. The idea of subsurface life has gained traction, particularly in recent years, after extremophiles were found on Earth, organisms that thrive in environments once thought inhospitable, such as deep-sea vents or acidic lakes. Subsurface oceans or aquifers could provide a stable and safe environment that protects life from the harsh radiation and solar flares that strike the planet's surface repeatedly. If Proxima B has a liquid water reservoir beneath its surface, it might increase the likelihood of finding microorganisms adapted to extreme conditions comparable to those on Earth, such as deep-sea organisms. In addition to seeking life, Proxima B also provides an opportunity to gain additional knowledge about broader processes that control planetary systems. The planet's location within the habitable zone of its star provides a unique opportunity to study the interactions among planets and their host star, and the ways in which these interactions impact the ability to maintain life. For example, the frequently occurring solar flares from Proxima Centauri may play a significant role in shaping the atmosphere and climate conditions of Proxima B. These flares could influence the planet's weather patterns and magnetic field, each of which is important in determining whether the planet can support life. Though Proxima B research is still in its infancy, technological advancements in observation, like the James Webb Space Telescope, JWST, are changing the game. Scientists can use JWST's infrared capabilities to conduct a more in-depth examination of the planet's surface and atmosphere for signs of habitability. As our understanding of exoplanets continues to evolve, Proxima B will remain a priority in efforts to answer one of the most profound questions in science. Is there ultimately life beyond Earth? The study of Proxima B is not just about finding alien life, but also about gaining a deeper understanding of the conditions that make a planet habitable. By understanding the elements that go into a planet's capacity to sustain life, scientists can apply this knowledge to other exoplanets in the future, extending our search for a place to live in the universe. The exploration of Proxima B is only one step on a long road to discover the vast and enigmatic expanse of planets outside our solar system. The research into Proxima B also contributes to our comprehension of the formation of planets and the emergence of new star systems. By analyzing the connection between Proxima B and its host star, Proxima Centauri, astronomers can gain insights into the dynamics of closely orbiting planets. These stars, situated around red dwarfs, which comprise the majority of stars in our galaxy, present distinct difficulties and opportunities for the formation of planets.